Okay, this is a talk I've done a few times, and it fits 30 a little better than it does 20, so we'll go a little fast. But if you have any questions, and we get a lot of industry-specific questions for these, feel free to find me outside or at happy hour or something like that. So without further ado, let's get into it. So the first pitfall, feels like a novice thing, but this really pervades everything you do, train versus test. So what that means is you don't want to look at the training data to think of how good your model is, and we continue to see this even in people interviewing. That you want to separate a part of your data set and not have your machine learning model look at it, because it will start using all of that in the wrong way. It will start to overfit. So this is how you protect against the general quality of overfitting. And the most common way is just, again, separating it. Either a single holdout, we'll see some other strategies that are a good idea, but you really only want to look at how well your model, so everything the machine learning model looked at, how well that translates to the data it didn't see. That's how you work in production. Future data, usually time is a good way to split things. But I personally almost never look at the training. In H2O, we actually have a little chart here that this is coming from Elements of Statistical Learning, but we have charts like this in H2O for the models, and the red line is essentially what I look at. The blue line is what the model sees. And so this is what a lot of people will talk about when they're looking at AIC, BIC, different R-squared of your model, things like that. It's the blue line. It's how well it fit the data that it saw. I don't really care. I need this thing to work on future data. And so the red line is what I care about. And the difference here, so the red line is you're going to watch these curves. This is kind of like a GBM curve. They all have different personalities almost, but random forest tends to head straight down and then flatline. It's hard to overfit a random forest. Deep learning will look a little more like this in GBM. I use GBMs a lot. What you're really looking for with the model is, we're assuming the x-axis here is iterations of your model. You can think of complexity if you want to, but it tends to be trees for a random forest in GBM. So as we see this thing move, you can see the red line starts to actually go up. So most of these models will continue to get better no matter what. GBM will keep fitting, but I don't really care. At some point, it's fit too much, and I need to know what that point is, roughly. And so I don't necessarily care whether it's 20 or 21 trees is the right place to stop it, but that's what I want to look at. And in fact, now we have that built into H2O, so you can actually use stopping rounds, and it will go find that point for you. So you can do your validation in one shot. And so actually don't even really think about this, which is nice, because it's one of the parameters you spend the most attention to unless you use a technique like this, where the model just handles it. So H2O is built so you don't have to worry about figuring out the model complexity, but the overall principle is definitely you want to look at how well this works on data the model hasn't actually seen. Validation set is one extension of that. So we usually advocate a very iterative process. That means you're running a lot of models. The models themselves are doing a lot of things. And so after a while, you're kind of biasing even your own estimate. Let's say we do, I think on the last slide, I think we said, for example, a 70-30. Maybe 90-10 is more of what I do in practice if I'm using that. Usually use cross-level validation. But in any case, after a while, if I've partitioned 10% of my data, and then I've run 500 models and gone weeks or months, continually hitting that 10%, eventually you've overfit that set as well, just in the way that you're acting. So you want to protect against that. Sometimes a good way to do that is to get an additional partition. So maybe instead of a 90-10-10, you split an 80-10-10, and you model on the 80%. The next 10% is your validation. And then when you're done with your entire process, you make sure you get something quite similar with that other 10%. It's tough to know what to do when that goes off. It's almost kind of like you have to start from scratch. Something you did peaked a little too hard, and you kind of have to redo that process to a certain extent. Hopefully you learned a lot that can help you skip ahead. But this is one additional test. I mean, you see financial modelers almost lock and key. There's additional data sets that you cannot peek at, and they will use that to train how well your model translates to the future, things like that. So that's pretty important, too, if you're doing this machine learning process over and over and over. And it's easy to forget for some of those like us that do the competitions. Kaggle, the competition vendor, is acting as that final be-all test set. In practice, you kind of need one yourself because to keep yourself honest. Model performance is kind of an umbrella slide. And so what to do here, wrong is there's many different ways of doing that. But again, we have the test error. It kind of brings in that first slide. K-fold cross-validation is a good way, other than what I'm kind of saying, 80-10-10, 90-20, whatever, or 90-10, whatever you're doing there. And I should also say, the nice thing about a lot of these slides is we've made that easier for you to do. So we have k-fold cross-validation. It's an n-folds parameter inside all your model APIs. We also will let you sample your data frames up front. So if you want to do an 80-10-10, you can keep a hex frame out there as long as you have the cluster up. And we'll take a training set and a validation set. So it's an incredibly easy way to actually carry out, so you don't have to make these mistakes. And so it's so easy to use that it's nice. I don't have to write any code to do it. I just drop something in. And we also have a folds column. Sometimes you have data sets that are partitioned a very specific way, and you want to make sure and adhere to that partitioning scheme, whether it's time-based or just something else. Like I don't know which market I'm going to enter into, so let's run a model that's seen all the markets but one. Folds column is how you can execute that. But also with model performance, so I think, and there's another slide that gets to this too, but performance metrics, we've seen some people use R² as if that's the best way to evaluate all models. We do support it. You're going to see an R² out of classification and regression techniques. But what you really want to do is figure out what makes sense for your problem. So here we have regression, R², MSE, RMSE is kind of the same things. Really should update this. And MAE, absolute error, is a really good one for regression. That would be robust statistics. And it's nice for getting quantiles and things like that. But you can think of median house price is the most common thing to do because that distribution is so large, and the high end in particular can dominate a mean. So you want to be thinking about whether that's true of your problem too. A lot of times if your data set scales more than one order of magnitude from the min to the max, it's worth considering the robust statistics. Really just think about how you're going to evaluate your problem, especially if how that's evaluated at the end of the line. When people are actually viewing your application or whatever it is, whatever they perceive as accuracy, you should try to match that as best you can with how you're evaluating your models through all of these loops, so this entire iterative process of modeling. Classification, there's a lot of ways to pay attention. This is difficult. There's definitely no right way to do this. A lot of times you're kind of paying attention to more than one. So we have straight accuracy. That's, a lot of people, it seems the simplest. It's probably one of the worst ways to do it. F1 is a balance of how well recall and precision are coming in. So recall is how many of those that you found of all the positives. Precision is of those that you called positive, how many of those were correct. F1 is a nice way of balancing that. Log loss is for calibrated probabilities. So that, as opposed to like an F1 measure, which is balancing where your threshold is. Log loss is how well everything's calibrated. And I find that an interesting one. Not a lot of people are familiar with that out of the competition space, maybe. But it's for, first of all, if you're doing logistic regression, either yourself or under the hood, because that's what most of our models do, that's how they work. And so it's actually kind of nice. That's what we're going to plot for the most part. But it's a nice way of saying, if I'm saying this is 98.2% accurate, with judging log loss, that's as well calibrated as you can get. Improvements to your log loss are going to help you with your calibration of how well those probabilities are shown to the end user, if that fits your use case. But AUC is a really popular one because it's agnostic for most problems. It's just how well it's sorted. It doesn't care about calibration at all. There's no threshold needed for recall precision. So it's actually very standard. It's very easy to use. But if you're not doing a ranking sort of thing, it's good to know. It's a nice bearing to have of what your model is. For a ranking problem, it's actually exactly what you want, because it is going to tell you the best things are generally floating to the top. And that could be right. If you're prioritizing resources, that's generally what you want to do. I have enough for 500 work items. Here's my best 500. Let's go. Well, AUC is going to be a good way of ensuring that you're sending the best 500 to whoever is actually working on those predictions. Class imbalance, a little more technical. So this would be classification. A class imbalance is where you just have either a binomial, in the simple case, trues and falses, and you have a very low rate of one or the other. Maybe you have dominant, most of the time it's dominant negatives, but it doesn't really matter either way. And it says eventually, it'll say there's no precise definition. So is 10 to 1 technically imbalanced? Is 100 to 1? Really what you could say is different algorithms perform different ways. Like SVM has a tendency to not find anything with even a minimal kind of class imbalance. GBMs, I don't really get worried until maybe it's like 1 out of 500 or 1,000, something like that. But what people do to kind of rectify the situation, and actually, let me state again, what you're really missing is the algorithm, the way it proceeds is just not going to it's not the best way of handling the data to get what you want. And the best reason to be worried about this is if a precision or recall metric is important to you. So the models are still going to go about their probability estimation. They may improve, if you can balance the classes a little bit. But the big ones that are different is if you need to recall something. Like you want to find, you're going to have a high false positive rate, but you need to find something. It can help to change the class probabilities. And so we have a class imbalance button. There's a balance classes in there. You can adjust the rate. And what that's really doing is you can either oversample the negatives, or you can undersample the positives. And so we'll let you pick the rate and how you want to handle that. But this is very common, and it's interesting. There's a metric we don't really talk about, but we started implementing, which was the average class accuracy. And that's that's a good method for when you have a really dominant class. They're almost always going to have a fantastic accuracy, log loss. All these things are really good because it can pretty much just guess the majority class and be almost right. But looking at the accuracy per class and almost unweighting it, you can think of just changing the weights to where 1 for every class. That's an interesting way to look, and we have one of these live for people where we're looking at about 65 different classes, and we want to make sure that it can find some of those minority classes. And that's where you want to start looking at the class imbalance a little bit. Clickstream people know this all too well. It's incredibly low rates of positives. So downsampling the positives is probably the simplest thing to do. But it depends, and you can try things out, and H2O kind of makes that as easy as we know how. One trick that can happen if you do this, if you hand roll this, you want to make sure that you don't adjust the balancing, you don't rebalance your validation test, because your validation set, and we do that as well. So we'll show you how good it is on an unbiased sample of whatever you chose for your validation sample. And that's important because in the future, you're not going to get this clean distribution of ones and zeros. And you want to make sure however you're scoring yourself matches that as well. Kind of mentioned, some of these remedies. We heard today earlier, someone was mentioning that SMOTE is in one of the scikit-learn utility, the way they're doing the parallelization. I forget Taylor's thing, but the package he's got, but that's kind of cool that they implement. SMOTE often comes up. That's synthetic, minority oversampling technique, kind of popular to try and be a little more precise. It handles all the categories differently, and it tries to create additional examples, not just by reweighting things, but actually changing the data a little bit. Categorical data can be interesting because there's so many different ways of handling that. So there's always these arguments. Do I do leave one out encoding? Not leave one out, but that's what Brandon was doing earlier, which is a good method. But one-hot encoding. So do I take my 4,000 different cities and create 4,000 columns, each with a 1 if it was there and a 0 if it isn't? That's a very popular way to do it. H2O handles these quite gracefully. So where we require that, which would be a linear model, where we require nice numerics, zeros and ones, which is going to be a GLM and a deep learning, we'll do that for you. You don't have to do anything. And for the tree models, they don't require that. So we actually have specific ways of handling all the categoricals that's very efficient. And the difference is you can read, when you read the feature importance plot, I prefer it this way because you can see that it handled that entire column all as one unit. When you one-hot all these, and if we go to an airlines data set, you're going to see a different feature for every airport, which means you're only going to see the top ones usually. So just different ways of doing it. It mainly says, there's no right way to do it. It could even make sense for a tree model to go ahead and one-hot it yourself. There isn't an inverse of doing that I know of for GLM. So categorical data can be tricky. You're also looking at how many classes is especially important. The deeper they are, the harder it's going to be to one-hot things and find a signal in there. So you may want to aggregate things, put things together. We have kind of take advantage of hierarchies that exist to you by grouping things together. Missing data always causes a lot of problems. We see a lot of people that go through one of our test sets that purposely has NAs there, and they spend so much time going over their NA handling, and then in the end, they run a tree model, which kind of doesn't care. But missing data it's definitely tricky. Definitely do want to pay attention to it. I prefer tree models because I don't have to pay attention to it, but in the end, I still want to. I want to know that it's doing the right thing. Types of missing, that's sort of missing can mean many things, and we see at a lot of transactional systems, NA could mean -999. -998 is a different type of missing, -997. People do crazy things to try to encode the information in one column of what is really going on here. So it could be that it just doesn't make sense. How many wheels on a boat? Well, that doesn't, I don't know. But we're going to impute the mean. Most people, let's give it 4. So is that useful? Not really for solving the problem, but at least it's not dangerous to your model. That's generally what people are trying to do. So a linear model is going to essentially give it no weight for whatever that mean is. So it seems it's a fairly safe thing to do. It also allows you to keep reading the coefficients. But other things of, even if you're going to do that, if you have 1,000 fields, hard to do this, but on a few fields, create an indicator field. If you're going to impute, maybe also add another field which says whether it was in A or not, and then you can actually see both things jointly. And that's probably a good idea anyway. Something that's kind of new to H2O is RNA handling. So we've always handled NAs, so you haven't had to work, I should say again, with tree models. With our GLM, you're going to have an option of how to impute it a little bit. But for the tree models, we've always had a dictated way that these are handled, but the latest, so Arno changed this a lot to make it actually figure out which of the paths down the decision tree for every split point is better at that point, which actually means you could be handling NAs dynamically, but in the way that makes the most sense and helps your model the most. So they don't necessarily go left, as you may have heard us say in the past. Now they go whichever way helps the GBM the best, and that's interesting. Outliers, another kind of thing like missing data. So outliers can be in the response or the predictors. I mean, the response is probably where you want to pay the most attention. So if what you're predicting has outliers, a housing price, and you want to figure out how to either get the 14 million house right, if you think that's important, more of what you're usually worried about is how to not do much damage with that $14 million house. So I can still have a reasonable approximation on everything else. Otherwise, it's going to drag all those predictions up. And that's not even a true outlier. If you had bad data, I mean, those are some real outliers, and you want to kind of handle that. So paying attention to these, what to do. So rare extreme events. So what happens is that, the models themselves, especially if you're focusing on like squared error for something, it's going to gravitate towards these outlier values. Because that's where your squared error difference is going to be the most. And a lot of times it makes the models almost meaningless for the bulk of your predictions. But sometimes that's right. If it's an expectation model, and that may be still correct to, on the average, guess this all the time. So you have to kind of know your problem with what to do here. But a lot of times people will either log the target, so log that housing price, and look at everything on a log scale. That will help, if you look at the distribution, it's going to look more like a normal distribution. And so usually something a lot of people just try out anyway. If they look at a histogram of their target and it looks like you've got a tail, you might throw a log or some transformation function to try to get it to be more of a normal distribution, particularly if you intend to evaluate your model based on squared error. And I'm already over time, sorry about that. Removing some of these, so we've got some extra stuff in H2O to make sure that we're precise about this. If they happen in the predictors, that can throw our distributions off in the past. We will compute a histogram, which is a min-max, and divide that into the bins, and outliers will have an effect there. So we have an option now for the histogram type of quantiles global. So if you see that it's something, for me, I just kind of try it out sometimes. It's pretty easy to use that in the modeling workflow. But that's aimed at handling outlier values, which could it can essentially make it where the model can't see the actual distribution of your column when it's trying to find a split point. Leakage, I'm very passionate about, especially when you get into feature calculation and trying to create additional features to help these models out. You do a lot of things like mean encoding, which you have to be very careful of what to do, but it can happen in other ways of how you pull your data. I always go this pulling data from a data warehouse, and you think this timestamp is good, but what you realize is there's a latency from the warehouse, so it said it was available at midnight, but it really didn't come in till 2. You got to be careful of that, and that's the subtle example, because I don't have a recipe for telling you how to realize that. You kind of have to know your data. When you go to predict at 12:01, your model was trained on something that always had that data, but really it's missing. The latency has come in, so guardrails is usually what we want to kind of put in. So we've kept an eye on that. A lot of discussions with some people in this room on how we can help you prevent this, that sort of thing. It's going to eventually show up that your distribution, when you go to predict, looks very different from your distribution of your training data. There's a lot of other ways that leakage can happen, but what you really want to do, and all the way back to slide 1, is make sure your train and test is done with a way that you intend to predict. You've got to mimic that as well as you can, and so it isn't always random. In fact, I find it rarely is. time is a nice and safe way to generally get that across. There's a lot of other ways. Sometimes you lose data doing that also if you have a small data set. So in the interest of time, useless models, what that boils down to is solving the wrong problem, like not spending enough time with the business and figuring out what they're really doing and thinking, I've maximized my model, here you go. And it comes out that, well, yeah, like we could have figured that out. You know, what we're really after is this thing over here. And maybe that means you're adjusting, you know, your data set, maybe you're adjusting your targets to look at something different so that the machine learning model optimizes something different. But I think there are a ton of useless models out there because people are just, they want to get going, running machine learning, and they're not spending enough time understanding what the real issue is. No free lunch, none of this stuff ever works. So, I mean, all the time is what I should say, sorry. It does work very well. You know, all these techniques, a lot of the assumptions, I almost grew up with GBM, I feel like, once I learned this stuff, because it did handle all these things, so I don't have to think about them. But it does, but you're better off also handling those on top. So you can get away from a lot of the assumptions these models have and these stories, oh, deep learning always handles interactions. Yeah, but if you hand it the interaction, it's going to do better almost every time. Lots of different models for lots of different purposes. And that's why we have a breadth of models in there. I mean, we haven't really mentioned much about the unsupervised models, but you know, I do use GBM almost like a sledgehammer, but I definitely try other things, and that's where H2O is nice. I've got my data set ready to go. Why not try a random forest? Why not try GLM? Why not try deep learning? It's as easy as taking my one predict call, swapping it out, fixing the parameters. And so I do that all the time. I'll work on a GBM a whole lot, and then a few lines below are my attempts at the other models. And if any of those look pretty good, I can keep on doing that. And sometimes they're better. Sorry for the speed, but again, definitely catch me out here if you have any questions about how this works. And hopefully H2O helps you kind of solve a lot of these. That's what we're really gearing towards.